So getting back to our discussion of kinetics, we've seen that over time, a reactant concentration decreases, like it does in the plot here, and product concentration increases. Well, this blue trace increases more quickly than this red trace decreases. Why? Because of that 2 out front in front of your products. But so far, we have no way to say precisely how much reactant or product is left at a certain point in the equation, in the reaction. We want to develop a way to say the concentration of the reactant is this after so much time has passed. Or we want to say, how long does it take for the reaction to be finished, or for the reaction to get to 90% of the reactant depleted? So those 2 calculations are 2 of the common calculations types that we will do, concentration as a function of time in this kinetics section. So we've seen a few times now that if we plot a reactant concentration over time, the reaction concentration decreases. But maybe that is how it decreases for a second order reaction. How does the concentration change for a first order reaction? It also decreases, but it doesn't decrease with quite the same slope as it does for a second order. And lastly, for a 0 order, it also decreases, but it decreases like that, as a straight line. So we need to develop different equations for concentration versus time, because it all depends on the reaction type. It all depends on the order of the reaction as to how the concentration changes over time. So here are the 3 most common rate laws. We have a first order, second order, 0 order. Let's develop some concentration time equations for these 3 reaction types. So if we start with a first order reaction, that rate law is rate equals K times the concentration of reactants raised to the first power. Well, back a long time ago, when we started talking about rates for the first time, we said the rate of the reaction could be expressed as the rate of decomposition of reactants over time. So if I just substitute in rate of reaction for rate of decomposition of products, rate of decomposition of reactants over time, I get this guy. That still equals my rate law. If I combine like terms, like this, bringing delta T along with the negative over to the other side and dividing by R over here, I can, stay with me here, integrate both sides of this equation. And the integral over here simplifies to, ln of R at time t minus ln of R at time 0. And that's equal to integral on this side, negative kt. So this equation is the concentration time equation, but it's specific to a first order reaction. This is not valid for second order or 0 order or any other order. This is the first order concentration time equation, and we will see it this way a lot. One other way that we will see it somewhat frequently is we will see it written this way. The reason one might choose to write it this way is because it takes on the slope-intercept form of a line. If you plot ln of concentration at some time versus t, you get a line with a slope of negative k. This is for first order. What's it like for second order? For a second order reaction, that says second, is totally not legible. Our rate law says rate equals K times the reactant concentration squared. doing the exact same substitution I just did for the first order, the reaction rate can be described as the rate of decomposition of reactants over time. Set that equal to the rest of the rate law. Combining like terms on each side. I get delta R over R squared equals negative KT, K delta T. Again, stay with me. If I integrate both sides, the integral here simplifies to negative 1 over R at time t minus negative 1 over R at time 0 equals negative KT. There's a lot of negatives there, so we can simplify this further by multiplying by negative 1 to get this equation. 1 over R at time t minus 1 over R at time 0 equals positive KT. This is the second order concentration time equation. It is often written in this format instead. The reason one might write it in this format, again, it's written in slope-intercept format. If you plot 1 over the concentration of the reactant versus time, you get a line with a slope of K, positive K. That's first and second. What about zero order? For a zero order reaction, my rate law says rate equals K times reactants to the 0 power. Substituting in delta R delta T for the negative, delta R delta T for the rate of the reaction, I get this. Combining like terms. Integrating, I know when I say that word, y'all tune out. I get it. Integrating from time 0 to time t, I get R at time t minus R initial, this little 0 is initial, equals negative KT. That's my 0 order concentration time equation. And you guessed it, I can write it in the slope-intercept form to look like this. For a 0 order reaction, I need to plot concentration versus time, and I get a line with a slope of negative K. So we've developed our 3 concentration time equations. One reason that they matter is because it's common to plot concentration versus time, ln versus time, and 1 over versus time with a set of data so that you can determine the order of your reaction. So if you plot concentration versus time and you get a straight line, it means your reaction is 0 order. If you plot ln of concentration of reactants versus time and you get a line, it means your reaction is 1st order. If you plot 1 over concentration of reactants versus time and you get a straight line, it means your reaction is 2nd order. So it's common to be presented graphical data and you have to determine the order of the reaction based on the graph. You need to pay attention to the y-axis. 1st order reactions, it's great. We can talk about their concentration at certain times, but a very common way to talk about them is what's called the half-life. A common way to talk about all reaction types is a half-life. Half-life means how long did it take for half of your initial reactant to be consumed. So you could look at the half-life of this reaction. If we started at 0.1 molar, after some amount of time, I end up at 0.05 molar, half of my reactant has been consumed. This specific reaction took 100 seconds to get there. So the half-life of this reaction is 100 seconds. Another half-life elapses. After 100 additional seconds have passed, you go from where you were at the start of that new half-life to where you were at the end of that new half-life. You went from 0.05 to 0.025. Every 100 seconds, your concentration is cut in half. This is a first order reaction. So let's revisit our concentration time equation for a first order reaction. If I go back to my first order concentration time equation, I can calculate how long the half-life of any first order reaction should be if I know one thing. Let's explain. I'm wanting to know half-life. That means the amount of time it takes for the initial concentration to become half of what it was. So if I plug in R0 over 2, or 1/2 R0, then I can simplify my equation. If I go back to pulling ln on the other side, ln of 1/2 R0 minus ln of R0 equals negative KT. Subtracting ln's is like dividing. So ln of 1/2 R0 over R0 equals negative KT. Cancel out my R0, ln of 1/2. ln of 1/2, doing some algebra that y'all may not love, ln of 1/2 is the same thing as ln of 2 raised to the negative 1 power. So why would I do that? Because powers can come out front in an ln equation. So negative ln of 2 is equal to negative KT. Oh my, if I'm losing you, that's okay. Hold on. Solve it for T. This is specifically half-life. I should have written that over here as well. T is half-life this whole time in blue because I'm plugging in 1/2 of the original. So my half-life becomes ln of 2 over K because my negatives can cancel out. So for this half-life equation is only valid for a first order reaction. So for a first order reaction, if I know how long the half-life is, I can calculate K. If I know what the rate constant is, I can calculate how long the half-life is. So back to our equation, this is first order. I know my half-life for this specific pink trace is 100 seconds. So ln of 2 over 100 seconds gives me a K, a rate constant value of 0.0069. As you've seen previously, the units on the rate constant are different depending on the reaction order. Sometimes the only indicator that you have that a reaction is first order is looking, or any order, is looking at the units of the rate constant. First order rate constants always have a units of seconds to the -1. So this is my rate constant for the pink trace. What if I compare the pink trace to a black one? This one has a shorter half-life. Here is when I reached the halfway point. That is when half of my reactant has been consumed, and that is a shorter half-life than the pink trace. There's my second half-life. The half-life for the black trace is 50 seconds. What if I compare that to this blue trace? The half-life for the blue trace is longer than the pink one. In fact, it's twice as long as the pink one. The longer the half-life, the slower the rate. So you could calculate rate constants for the black trace and the blue trace. But in general, the longer the half-life, the slower the rate. There's our rate constant for the black one. There's a convenient formula that says after the first half-life has passed, you have half of your initial concentration. After the second half-life has passed, you have 1/4 your initial. And the third, you have 1/8. And the fourth, you have 1/16. The convenient formula says that 1/2 raised to the n power, where n equals the number of half-lives, 1/2 raised to the n power times the initial concentration tells you the concentration after n number of half-lives have passed. Blah. So if we know that the half-life of N2O5 is 22.7 minutes, if it decomposes with that rate constant, if 0.2 of the original concentration remains, how many half-lives have passed? Our convenient formula for half-lives is this. And so if our question says 0.2 of the original remains, so let's say the original is 1 and 0.2 is what's remaining of that. So how many half-lives have passed? We're trying to solve for n. So 0.2 equals 0.5 raised to the n power. How do you solve when there's a variable in your exponent? LNs or logs, either one, it doesn't matter. Be consistent. ln of 0.5 n times. The reason I do ln or logs is because my variable can come out as a coefficient. So n equals ln of 0.2 divided by ln of 0.5. N equals 2.32. 2.3 half-lives have passed. So all three of those concentration time equations that we saw were concentration of reactants only. That's the only thing we could calculate there. What if we want to know the concentration of the products? We go back to our handy dandy limiting reactant tables. We know that we start with some initial pressure, because this is a gas, we're doing pressure. Some initial pressure of that gas, it's going to decrease by x over time, while the product increases by 2x over time. Solving or filling in my last row with variables there. How do I find what's the concentration of my reactant at some time later? Well, knowing this is a first order reaction, you solve the first order concentration time equation to find the concentration of your reactant at some time t. So from there, you can fill that in as your x value to say the product pressure is equal to 2 times the initial concentration of gas, initial pressure of the gas, minus 2 times the pressure after some time t. What do we do with all these formulas? We solve problems like this. So here's our given equation. For the decomposition of N2O5, the rate constant is this. What order is this reaction? First. How do I know it's first order? Sometimes the only hint you get is the units on the rate constant. Seconds to the -1 tells me this is a first order reaction. So this first order reaction, I can do some concentration time stuff with it. If the pressure starts out at 800 millimeters of mercury, what's the pressure after 200 seconds? I can find the pressure of N2O5 at 200 seconds. That's my first goal. How do I do that? Well, pressure and concentration are interchangeable, so the ln of the pressure at 200 seconds is equal to negative 0.007 times 200 seconds plus ln of 800 millimeters of mercury. Yep, I squeezed it in there. It's totally not legible. If I complete the whole left-hand side of that equation, do the math for the whole left-hand side, I get 5.284. That's equal to the ln of pressure in 205 at 200 seconds. Yep, that is totally not legible. I do the e to the, oops, I forgot my negative. Nope, I did not forget my negative. Sorry, that math is correct. I e to the, and I get pressure in 205 at 200 seconds is equal to 197.3 millimeters mercury. That's my pressure of my reactant. But my question says, what's the pressure in the container after 200 seconds? So here's where my ice table comes in. I'm going to rewrite the equation down here for ease. Our equation sadly did not have physical states, but it should have. They're all gases. I started out with 800 millimeters of mercury initial pressure. None of this, none of that. I lost 2x. I gain 4x. I gain x. I know in the end, I've got 197. Let's leave off that decimal just for convenience sake. 197 millimeters of mercury at the end at my equilibrium in my final. Maybe we should make that an F instead of an E. So I can solve for x. 800 minus 2x equals 197. Negative 2x equals negative 603. X equals 301.5. So what's my pressure of O2? 301.5. And my pressure of NO2 is 4 times 301.5, which is 1206. 1206 millimeters of mercury. Ugh, we're almost at the end. This says, what is the pressure in the container? That means P total. P total is the summation of the entire last row of your limiting reactant table. So I sum those up and I get 1704.5 millimeters mercury. In my final chamber, I have a pressure of 1704.5 millimeters of mercury. That's enough for now. See ya.